This is General Physics 2, Week 10. This is lecture part 6. Why don't we just use DC for the power system? That's the basic question I'd like to ask right here. And in fact, this is what Thomas Edison was in favor of when he first started providing power for people, setting up generating stations and such. He was a big advocate for using DC. Why don't we do that? Why do we have to mess around with all this AC stuff? Why not just have everything provided with DC voltage? It seems like things would be simpler. Well, let's consider this a little bit. Here's an average house, and if it's got 120 volts provided to it, in the house, if people in the US use something like 800 or 900 on average, can vary quite a lot, but that's kilowatt hours per month. That's about 2,400 watts on average. That's the amount of power that you're using in your house on average. It gets a lot higher at some times and lower at other times. 2,400 watts at 120 volts means you're using on average about 10 amps of current. So 120 volts and 10 amps gives you the average amount of power that you're consuming in your home. Now, if we imagine that we're going to have a power station connected up like this, just directly, so that the generator over here would be generating 120 volts DC, and your house would be using 120 volts DC, and this 10 amps would flow straight from the generating station. That's fine when there's one house. What happens when you start adding houses? So Goshen has a population of about 30,000, and that's about 10,000 houses, maybe. And so 10,000 houses, each of them using 10 amps, presumably you'd wire these all up in parallel. So everybody's got the same voltage applied to their house, and you wire them all up in parallel. What that means, though, is that the current coming from the generating station has to supply all these, so it's got to be the total of all of these currents. So 10 amps times 10,000 houses. Well, that'd be 100,000 amps. So the generating station has to supply 100,000 amps. And if it's any distance away from the city, or from most of the houses for that matter, many of these wires have to supply that much current, have to carry currents on that order, 10,000 amps. What size wire would that require, you might wonder? You probably don't have much familiarity with wire. In your house, you have something like 12 or 14 gauge wiring in various places, and that's intended to carry 15 or 20 amps of current. And so if you have several circuits on at one time, then you might be needing to handle a little bit more, but on average, it's not terribly much more than that. The wires that come into your house are a little bit heavier than that, and they can handle perhaps up to 50 amps or something like that. But anyhow, that's 12 or 14 gauge. I went looking to see how big a wire I could find spec'd, and I found a place where if you look up this stuff, these gauges that they have, 12 and 14 gauge, it's backwards. The gauge numbers get smaller as the wire gets bigger. And so you can get, 10 gauge wire is heavier and carries more current, and then there's 8 gauge and 6 gauge, all the way down to 0 gauge, and then there's double zero, and I suppose it's aught and double aught and triple aught and quadruple aught, AWG 4 aught. That's ½ an inch in diameter. So that's quite a thick cable, and that carries a whole whopping 300 amps. How are we going to get up to 100,000 amps? You might think it would just be by the area, and it is sort of, except it's not that good. In other words, if you double the area, you don't get double the current. You get less than that, because the heat can't escape from the inner parts of the wire very well. So this is a terrible problem. This is not going to solve things. Somehow, what we have to do is get away from having the same voltage everywhere. What we're trying to deliver is power. And what we want to do is somehow be able to deliver high voltage not just keep adding up more and more current. You can do it either way. Now, you might think, well, just raise the voltage. So instead of 100,000 amps, let's try to get it down to, a mere 1,000 amps. And so you'd have to make the voltage 100 times higher. 100 times higher would be 12,000 volts. I don't know about you, but I have no interest in having 12,000 volts anywhere in my house. Certainly not that I would be plugging things into on a regular basis. That would be exceedingly dangerous. So that's not going to work. Somehow we have to be able to switch different voltages, to be able to use high voltage to transmit the power across the country, and then switch down progressively to lower voltages as we get closer and closer to the houses, and as we have wires that are serving fewer and fewer houses. Out here on the big cables that are serving a whole city, we might want to have extremely high voltage so that we can carry the needed power. That's what we'd like to be able to do. But to do that, we need to be able to convert from one voltage to another. How do we do that?